Welcome to this explainer, where we're going to unpack the hidden science of the built world around us. We walk over bridges, fly in airplanes, and use our electronics every single day, usually without a second thought. But literally everything we touch and every structure we rely on is fundamentally defined by the materials it's made from. Today, we're taking a really close look at the DNA of those engineering materials and why choosing the exact right one can mean the difference between a towering achievement and a total, catastrophic failure. So, let's dive right into this mystery. Why did the Titanic actually sink? We all know about the iceberg, right? But the answer isn't just a physical collision. It's actually a massive failure of materials. The underlying engineering science tells us a much deeper, way more complex story about why that ship's hull failed so abruptly that night.
Here's the crucial point. The specific steel used to build the Titanic became dangerously brittle when it was subjected to freezing Atlantic temperatures. It wasn't just the sheer force of hitting the ice. The special chemistry of the steel itself, combined with the stress of how it was originally put together, created something called cold temperature embrittlement. The material literally changed its fundamental behavior just because of the cold environment it was sailing through.
Which brings us to part 1, the core of material science.
To make sure tragedies like the Titanic don't happen today, modern engineers rely on a highly structured approach known as the Core 4. Think of it as an unbreakable chain, where how a material is shaped and structured dictates exactly how it's going to perform under pressure. It all starts with processing, how the material is shaped and formed. That processing directly affects its structure, meaning the actual arrangement of its atoms. That atomic structure then determines its unique properties. And finally, those properties dictate its overall performance in the real world. It's a continuous, totally logical flow.
All right, let's move into part 2, the 5 material families. Pretty much every physical component you interact with falls into one of these categories. Now, what's really interesting is how composites sit right in the sweet spot of this family tree. They borrow the best strengths from metals, ceramics, and polymers. A composite is essentially just a hybrid where one or more mutually insoluble materials are mixed or bonded together. Think of everyday stuff like fiberglass, concrete, or even plywood. By combining layers or particles of different families, engineers can create a supermaterial that maximizes the absolute best traits of its base elements.
Now, looking at metals specifically, we see a really stark contrast between heavy, rust-prone ferrous metals and lighter, non-ferrous metals. Ferrous metals contain iron, which makes them magnetic, highly durable, and relatively inexpensive. They're absolutely perfect for things like massive structural steel beams in a skyscraper. But their major downside is that they rust. Non-ferrous metals, on the other hand, don't have any iron in them. They're non-magnetic, highly resistant to corrosion, and generally a lot more malleable, though they do tend to be pricier. Think of the lightweight aluminum used in a soda can or an airplane wing.
Moving right along to polymers, their absolute superpower is flexibility. Polymers are basically molecules formed by long chains of repeating units, and we categorize them into 3 main types. First, you have thermoplastics. These become pliable when heated and solidify when cooled, kind of like melting butter and letting it harden again. Second are thermosets, which are irreversibly hardened during their initial curing. If you try to reheat them, they won't melt, they'll just burn. It's very much like cooking an egg. And third, we have elastomers. These are highly elastic materials with properties similar to a rubber band that just easily snaps back into shape.
Ceramics, on the other hand, are the tough guys. They can withstand immense heat and wear. These are solid compounds that can feature metallic or non-metallic elements. So we're talking about glasses, cements, and clays. They offer excellent corrosion and wear resistance, incredibly high melting temperatures, and very low electrical conductivity. But as you might guess, their sheer lack of flexibility is a massive trade-off. They are highly brittle and prone to shattering, which is something engineers have to carefully calculate for.
And bridging the gap between conductors and insulators, we have semiconductors. These materials, which can be pure elements like silicon and germanium or compounds like gallium arsenide, have an electrical conductivity that sits precisely between a conductor and a non-conductor. You'll find them acting as the absolute backbone of modern electronics, powering the integrated circuits, transistors, and diodes inside almost every single digital device we use today.
So, that's the materials. Let's head into part 3, defining material properties. Okay, so we know the families, but how do engineers actually measure what these materials can survive? It is vital to understand that a property isn't about how big a piece of steel is. In strict engineering terms, a property is defined as the magnitude of response to a specific imposed stimulus. In plain English, it's simply how a material inherently reacts when you push it, pull it, heat it, or zap it, totally independent of its overall shape or size. Instead of drowning in endless data, engineers focus on a few key properties to test exactly what a given material can handle. Mechanical and thermal tests tell them the exact temperature a material melts, its specific hardness, or the exact yield strength, which is the point where it begins to permanently bend and fail. These exact measurements give engineers the absolute boundaries of what a metal, polymer, or ceramic can survive before it breaks.
A perfect example of a mechanical property in action is visible deformation. When you apply a massive downward load or physical force to a specimen, the material squashes and physically changes shape. Managing this deformation is exactly what engineers are trying to calculate when they select a material to withstand a heavy load. They need it to bear the weight without exhibiting excessive or dangerous deflection.
But physical load isn't everything, bringing us to part 4, thermal and electrical responses.
Beyond just physical crushing, engineers absolutely have to account for how materials react to invisible forces, like heat and electricity. A material might be incredibly strong physically, but if it behaves unpredictably when energized, it's a huge liability. When dealing with electrical properties, resistivity measures how strongly a given material opposes the flow of electric current. Think of it kind of like water flowing through a pipe. Resistivity depends on the intrinsic resistance of the material itself, how wide the pipe or cross-sectional area is, and the specific distance the current actually has to travel.
Conversely, electrical conductivity is exactly the opposite. It's how eagerly the material lets that electrical charge transport through it. If resistivity is the resistance to flow, conductivity is simply the reciprocal. It is the core property used to specify the electrical character of any given material, determining whether it acts as a conductor, an insulator, or a semiconductor.
Shifting gears to thermal properties, metals and ceramics differ wildly in their capacity to absorb heat from their surroundings as temperatures rise. Heat capacity essentially represents the energy required to produce a unit temperature rise, and the absorption curve for metals ramps up incredibly fast at lower temperatures compared to ceramics, indicating vastly different thermal responses to the environment around them.
Now, this next concept is a massive aha moment. Thermal expansion means most solid materials expand upon heating and contract when cooled. But the rate varies drastically. It's pretty wild. If you take a 100-foot span of lead, it increases in length by over 3 inches when heated by 100 degrees Celsius, while a 100-foot span of plate glass barely expands by 1 inch. If you combine these materials in a structure without properly accounting for this drastic difference, the structure will literally tear itself apart as the temperature changes.
And finally, we have thermal conductivity. This dictates the actual rate at which heat moves through a solid, traveling from the high-temperature side over to the low-temperature side. Knowing exactly how fast heat is transported across a specific area is absolutely crucial for everything from designing a safe oven in your kitchen to building a spacecraft that can survive re-entering the Earth's atmosphere without burning up.
Because at the end of the day, the next time we push the boundaries of engineering, it will be our mastery of these very materials that keeps us safe. We've seen how the Titanic fell victim to an invisible material property flaw with cold temperature embrittlement. So, as we look to build the next generation of spacecraft, renewable energy grids, and towering skyscrapers, the ultimate question remains, are we truly understanding the hidden DNA of the materials we're building our future on?